Hi everybody, I'm back, Professor LaShan. I'm back to talk about section 5.4 and shoot some video. And I'm sorry about the buzz in my video, but I'm not sure what's going on with that. And my husband, my tech support person, is not available to help me figure it out. So we're just going to have to live with the buzz until he can help me. So in section 5.4, we're going to work with the central limit theorem. And we use that if we have a sample size of 30 or greater, which is considered a large sample, or the population we're drawing from itself is normally distributed. And when we use the central limit theorem, and there's a very long explanation, but basically it allows us to compare the mean of a sample, x bar, to the mean of a population. So we're going to use what we call the longer Z formula. And again, on the formulas page that I put in the to-do list for each of the weeks, this comes up in this week, week 12. You've got this longer Z formula, which converts a sample mean x bar into a Z score. But what's really important is when you're doing this, when you're putting it in your calculator, you're going to need to put parentheses right here to make this work out. And it's also tricky to use this, find the square root. So play around with finding the square root of something like the square root of 36 and make sure you know how to do that in your calculator, whether you have to hit second or shift or something like that. So to go right to the problems, we're going to go to example 4 on page 266. This is like what you're going to see in your homework in your quiz. And by the way, the chapter 5 quiz is all of chapter 5. It's a long quiz. The chapter 6 stuff, that'll be with 6 and 7 together on a quiz. So this is 5.4. So it says, and I'm on page 266. It says the figure at the right, it shows some little red cars, shows the mean distances traveled by drivers each day. You randomly select 50 drivers. So that's our sample size, 50, which is greater than 30. It's considered a large sample. Age 16 to 19. So that's the first car, the first driver. And what you see there, the first set of drivers, is you can see that the average miles per day by 16 to 19-year-olds is 20.7 miles. That's our population mean from the little drawing there from example 4. What is the probability that the mean distance that the 16-19-year-olds from your sample of size 50 traveled each day is between 19.4 and 22.5 miles? So the sample mean, x bar, is between 19.4 and 22.5 miles. And it says sigma, which is the population standard deviation, is 6.5. So as we talked about before, it's really important to draw the picture. So we're going to do that next. So we're going to draw the picture here. And in the middle goes the population mean, just as we saw in previous sections. And our population mean, remember, is 20.7. So in a large sample, the mean of the sample should be really close to the population mean of 20.7. So x bar of 19.4, that's less than the mean. And it doesn't seem like it's that far away from the mean, but we're going to put it to the left because it's less than the mean. Looking for my blue pen. Here we go. So 19.4 is less than 20.7. It's to the left. And we don't really have a good feel for how far to the left. Just put it to the left. And 22.5 is more than the mean. That's to the right because that's more than 20.7. And it's telling us to shade between. So we're going to calculate z-scores, but this time using that longer z formula because we're comparing sample means x bar to z-scores. And so we're going to do this twice. So we're going to start with x bar is 19.4. That should have a negative z-score because we're to the left of the mean. So x bar 19.4 minus the population mean mu 20.7 over sigma 6.5 over the square root of the sample size 50. So this again is a complicated calculation that you have to be able to do in your calculator here. So first thing you want to do is subtract 19.4 minus 20.7, which is going to give you negative 1.3, and the z-score is going to be negative, over 6.5 over the square root of 50. So this is what you have to be able to put in your calculator, and you want to use parentheses in your calculator. And so the way you're going to go to your calculator is you're going to do negative 1.3, and you'll probably already have that in your calculator, divided by, that with that fraction bar, left parentheses, 6.5, and again divided by, however you put in the square root of 50. Some of you would put 50, then square root. A lot of you will do second or shift, square root, then 50. So we're going to do the square root of 50 write parentheses, and then enter or equals to get your answer. And this is going to give you negative 1.414 something. And so we're going to round to 2 decimal places because that's how our z-scores are. So rounding to 2 decimal places here, we're going to end up with negative 1.414. We're going to keep the 1 and call that negative 1.41. Now we're going to calculate the z-score for x is 20, x bar mean, sample mean is 22.5. It will be positive. So x bar 22.5 minus mu population mean 20.7 over the standard deviation sigma 6.5 over the square root of the sample size 50. So this is going to give you 22.5 minus 20.7 gives you 1.8 over 6.5 over the square root of 50. Just like before, you've got to put this in your calculator with parentheses, otherwise you get the wrong answer. So you're going to do 1.8 divided by, left parentheses, 6.5, again divided by, however you put in the square root of 50, which might require to hit second or shift. So square root of 50, right parentheses, enter or equal, and you get 1.958 something. So we're going to round to 2 decimal places, and our z-score is going to be 1.96. So we're going to look them both up in the z-table. So we're going to start on the negative z side. We're going to first look up our z-score of negative 1.41 on the negative z side. And so looking this up, we have negative 1.4 row and then 100th. We get the area to the left, in the left tail, 0.0793. So let me put that in my drawing here. This is 0.0793 because the table gives us the area to the left. When I look up my 1.96, I'm going to get the area to the left of 22.5, to the left of a z-score of 1.96. So I'm going to go to the positive z-table, row 1.9, and then I'm going to follow down until I'm under 600ths, and I'm going to get 0.9750 for 1.96. That is again the area to the left, 0.9750, all the way to the left tail. So to get our answer for this question, we're going to take 0.9750 minus the unshaded part in the left tail of that of 0.0793, which is going to give us our answer here of 0.8957. Sorry, rather than using my calculator, I just looked in the book here. 0.8957. So the probability that a sample of randomly selected 50 randomly selected 16 to 19-year-olds are going to be driving between 19.4 and 22.5 minutes, which is not very far away from the 20.7 population mean, each day is about 90%. Because again, the mean of a large sample should not be very far at all from the population mean of 20.7. So going to the next page, going to example 5, which is on page 267. Let me take my board away here. Page 267. This one says the mean room and board expense per year at a 4-year college is $10,453. That's our population mean. You randomly select 9 4-year colleges. So, our sample size is not 30 or greater, so we need to keep reading here to make sure we can use the central limit theorem. What is the probability that the mean room and board expense is less than, from our sample, less than 10,750? So sample mean x bar less than 10,750. Less than is going to tell us where to shade when we draw the picture. Remember, our sample size was not 30 or greater, so let's keep reading. Assume that room and board expenses are normally distributed. So it doesn't matter, actually, that our sample isn't 30 or greater because we have a normally distributed population. And it says the standard deviation, that sigma, is 1,650. So again, let's draw the picture. In the middle goes the mean of our population mu of 10,453. Our x bar of 10,750 is more than that. So it's to the right of the mean. You don't really have a good feeling about how far to the right. Just put it to the right. So 10,750. And less than means we shade to the left. All of this area to the left. Less than is always the easiest question because when we look things up, we get the area to the left. So we're going to calculate a z-score using, again, the longer z formula, x bar minus mu over sigma over the square root of n. Why the longer z formula? Because we're comparing the mean of a sample to the mean of the population. So longer z formula. We expect this z to be positive though, because our x bar is to the right of the mean. So we take x bar, 10,750. Let me put it down here so we can see it a little bit better. Sorry. So we're going to take x bar, 10,750, minus mu from the population, 10,453, over sigma, 1,650, over the square root of n, 9. So doing our subtraction in the numerator, 10,750 minus 10,453, we get 297 over 1,650 over the square root of 9. Now remember before when I said you have to use parentheses? That's important, but the square root of 9 we can actually figure out. That's 3. It comes out exactly. And so if you can make things easier on yourself with the calculations, I would do that. And I'm also going to check, does 1,650, does that divide evenly by 3? It actually does. So if you can make your calculations a little bit easier, I would do that. So this would be next anyway because of the parentheses, and 1,650 divided by 3 is 550. So to get my z-score, I'm going to take 297 divided by 550. Sorry, let me do that again. 297 divided by 550, and we're going to get a z-score of exactly 0.54. So no rounding required, which is great. And so we're going to look up on our positive z side, we're going to look up a z-score of 0.54, which is going to give me the area to the left. So if I go to row 0.5 and then 400ths, I get 0.7054, which is the area to the left of whatever I looked up. That's here. All of this is 0.7054. Is that our answer? Yes, that's our answer because we wanted the area to the left because it said less than. So 0.7054. Be sure when you're using My Stat Lab that you put 0 point for your answers. So one more example I want to walk through here, which is example 6, which is on page 268. This one says some college students use credit cards to pay for school-related expenses. Probably lots of us do that, right? For this population, the amount paid is normally distributed, so we can apply all our normal distribution formulas and everything, with a mean of $1,615, which is the amount of debt, and a standard deviation, that's sigma, of $550. 1. So we actually have 2 questions here. What is the probability that a randomly selected college student, that's just one student, who uses credit cards to pay for school-related expenses paid less than $1,400? So it's just one student, not the mean of a sample, just one student paid less than $1,400. So let me draw the picture here. It's always good to draw the picture. In the middle goes our population mean of 1,615. Where is 1,400 in relationship to that mean of the population? It's smaller, so it's to the left. Again, we don't have a real good feel about how far to the left. And less than means we shade to the left tail, which again is always the easiest kind of question then when we're calculating. So let's calculate a z-score, but this time we're using the shorter z formula because we're only converting a data value x into a z-score. So we're going to take x 1,400 minus mu 1,615 over the standard deviation 550. So if I take that, I'm going to get negative 215 over 550, which is going to give me negative 0.390 something. So rounding to 2 decimal places, we're going to keep the 9 and call that z-score negative 0.39. So Let me move that up so you can see that. That would be helpful, right? So calculating that, we took 1,400 minus 1,615, which is negative 215, divided by sigma, the population standard deviation, 550, which gives you negative 0.390 something, rounding to 2 decimal places so we can look it up in the table, negative 0.39. Let me grab another board here. And so we're going to go to our z-table on the negative z side, and we are going to look up that z-score of negative 0.39 on our negative z-table here. So I'm in row, whoops, sorry. I'm in row negative 0.3. Messed up my camera. Row negative 0.3. There we go. And then 900ths. So negative 0.39, which gives you 0.3483, which is the area where? To the left of whatever we looked up that z-score. So 0.3483, when we look up negative 0.39, is the area to the left, in the left tail. 0.3483. So going back up to the drawing, that's what we wanted, the area to the left. So the answer, the probability that a randomly selected college student would have less than $1,400 in debt when the mean of the population is 1,615 is about 34-35%, not unusual. So now we're going to go from example 6, we're going to go, that was question 1 by the way. Now we're going to go to question 2 from example 6, which says you randomly select 25 college students. So even though our sample is not 30 or greater, remember it came from a normally distributed population, so we're good to go with the central limit theorem. You select 25 college students who use credit cards to pay for school-related expenses. What is the probability their mean amount paid is less than $1,400? I guess it's not their debt, it's the amount they're paying. So less than $1,400, but this is the mean of the sample is now going to be less than $1,400. So let's draw the picture. So mean of our sample, or mean of our population, sorry, is 1,615. Sample mean 1,400 is going to be to the left, probably farther away than it was before, and I'll explain why in a second. But remember, the mean of the sample should not be so far from the mean of the population in a large sample or a normally distributed population. So now we're going to calculate the z-score, but this time we're going to use the longer z formula because we are converting a sample mean x bar into a z-score. So, and we expect it to be negative, our z-score. So x bar is 1,400 minus mu, population mean 1,615, sorry, over sigma. If we go back to the previous one, sigma was 550, over the square root of our sample size is 25. So remember, this was 215 over 550 over, well, the square root of 25 is 5. So if we can make that easier on ourselves, I would do that square root. Next, we would do parentheses there, but that actually divides evenly. So again, make it easier on yourself. This is negative 215 over 110. So when I divide that out on my friend's calculator, I get negative 1.954 something, and we're going to round to 2 decimal places. So we're going to call that negative 1.95 for our z-score, which we're going to look up, which is going to give us the area to the left, because that's how our z-table works. So we're going to go here. We're going to look up negative 1.95 on the negative z-table, on the negative z side, row negative 1.59, sorry, negative 1.9, and then 500ths, which is going to give you the area to the left, 0.0256. So much smaller than before. So the area to the left that we shaded was 0.0256. Let me move that down so you can see that. That's our answer. That's the probability that if we took a sample of 25 college students, the probability that the mean of that sample would be less than 1,400 is only a little more than 2%. So unlikely, unusual. And so there's one more question which says, compare those probabilities. So if we go back to our previous example here that we did, not sure where I stuck it here, but the previous answer that the probability that one person would have a debt of less than 1,400 was about 35%. There's a lot of variability between the mean of the population and the mean of a sample, so that's likely to happen. Between the mean of the population and an individual data value. So that was here. That was the part for answer number 1. So it's likely that if we picked one person, their debt would be kind of far away from the mean of the population. However, if we pick a sample of size 25, which is getting close to a large sample, but it was from a normally distributed population, the probability that the mean of that sample would be so far from our population mean of 1,615 is just not very likely. And so it's only about 2-3%. It's not likely. And so what they're saying is the interpretation is it's going to be unusual or unlikely that the mean of our sample would be so far from the mean of the population. So that's it for 5.4. I hope you enjoyed it.